Hi, everybody. We're doing 4.6 now, which is one of my, again, I happen to love chapter 4. I love a lot of stuff. And I mean, I like all of calculus, but these particular problems, the optimization. Um, Optimization we're going to see is doing things in the most efficient manner or getting the biggest bang for your buck and so on and so forth. But before I do that, I just want to point out, where am I getting the textbook that I'm showing you? So when you click on a problem in Math Excel, you click more help. You click that right there. That's the textbook. I'm going to click that in a minute. But you can also, if you click here, it says ask my instructor. I was kind of explaining this before. You could write a message, help, or whatever. You could write a message, and it will give me give me a link to the problem you're on. You're right there. See, it says section 4.6 question, whatever it is. So when it comes, I'll actually get a whole link, which I can click on, and it'll give me a clickable link, and then I can see the problem you're talking about. So you don't just so you don't have to explain every aspect of the problem. You could just say what your one little question is. You may have just one very specific. I don't mean little unimportant. I mean little like specific. You may have just a very specific question, and then you just click send. And then what will happen is that when I check my email, when I check my Gmail, it'll be in there, and I'll see whatever your question is and blah, blah, blah. So that's just an easy way for you to get in touch with me if you have a problem on a homework problem. And very often I could just answer it in an email. Sometimes it might be a little more involved. I could make a whole video on it, or I could do a Zoom chat with you. I could do Zoom, I could always do a private Zoom thingy ding with you, and everything's cool. Anyways, moving on. So so when you click here, it says textbook. That's what I've been clicking on every day before I start the class. And this is what you've been seeing me start with. There you go. So now we're doing 4.6 optimization. Okay, so optimization is as follows. Well, here's an example. A homeowner has $320 to spend on building a fence around the rectangular garden. 3 sides of the fence will be constructed with wire fencing at a cost of $2 per foot. And 4th side will be constructed with wood fencing at a cost of $6 per foot. So that one side is wood, the other 3 sides are wire. Find the dimensions and area of the largest garden possible, but the largest garden that can be enclosed with 320 feet worth of fencing. So we have a couple of restrictions. We're restricted by a certain price, and so within a certain budget, we want to get the largest area, because maybe he wants to grow flowers or grass, or whatever he wants to grow in there. I don't mean marijuana, I meant grass. Like please keep off the grass. And so what we're going to say is that this rectangle, right? So one side is X and the other side is Y. The length is X, the width is Y. So the area of this rectangle is X times Y. So A equals XY. Now the cost is going to be 2Y plus 2X plus 2X plus 6X. Why is that? Because this length Y costs $2 per foot. That X costs $2 per foot. That Y over there costs $2 per foot. But this X over here is made out of wood, so it's $6 per foot. So in total, it winds up being 8X plus 4Y. So the cost is 8X plus 4Y, and we want the cost to be, the cost has to be $320. So we want XY, we want the area to be a maximum, and the cost has to be specifically $320. So all I'm going to do is take the cost, and I'm going to set it equal to $320. Now, I know that XY has to be a maximum, so I'm going to do something so clever. Let me move my picture out of here. Okay. I'm going to do something so clever. I'm going to solve for Y in this equation. So 8X plus 4Y equals 320, 4Y equals 320 minus 8X, Y equals 80 minus 2X, because I divide everything by 4. Now I know that the area is XY, and I want to maximize that, but the area is X times y, but y is equal to 80 minus 2x. So I'm substituting in y. So the area is 80x minus 2x squared. Now, this is where the calculus is going to come in. Well, before I do the calculus, x, the smallest x could be a 0, so it has to be bigger than 0. And, y has to be bigger than 0, which means x cannot exceed 40. So x can only be between 0 and 40. Okay. And I want to find the biggest, the maximum value, I guess the absolute max in that interval. Well, guess what? This is a straight up calculus problem that we learned in the last section. I'm going to say y equals 80x minus 2x squared. I'm going to take y prime, or in this case, a prime, and I'm going to get 80 minus 4x, which means 80 equals 4x, so x equals 20. 20 is my critical number. And I know that the function a is continuous on the interval from 0 to 40. So the absolute max of a is either going to be x equals 20, or it's going to be when x is one of the endpoints. So if x equals 20, then y is equal to 80 minus 40, which is 40, and 20 times 40 is 800. And we must answer the question. So the maximum is 800. By the way, what about you have to check the endpoints as well. But as you can see on table 1, the endpoints just want it being 0. So the endpoints are easy. The only viable thing is the x equals 20, which gives me an area of 800. So the maximum, so the dimensions that is going to give me the best thing is going to be 20 times 40, and one of the 20 foot sides is going to be the wood part, and my area is going to be 800. So I'm going to get 800 square feet of planting out of this, and it's going to be 20 by 40, and the wood part is going to be 20 feet. And that, my friends, is the story. And so this is the basic strategy. This is just summarizing what we already said. Okay, what about minimizing? Just like you can maximize, you can minimize, because depending on what it is that you want. So the homeowner judges that the area of 800 square feet is too small and decides he wants an area of 1250. What is the minimum cost of building a fence that will enclose a garden with an area of 1250? And what will be the dimensions? We want to find the dimensions for x and y that's going to enclose 1250, but the cost is going to be a minimum. So what dimensions is going to make a minimal cost? Well, we know that the cost is 8x plus 4y. We're using the same diagrams that we had on the previous example. And now this is subject to. Subject to means this is a fixed thing. XY must equal 1250. That's a must. And this is the part that's more variable, because I can still move x to y. As long as xy is 1250, I can look at all different possible combinations, but I want to get the minimal cost. I want the cost to be the least. Well, if xy equals 1250, I'm going to say, well, y, I'm going to solve for y, but I'm going to solve for y in this equation, not the other equation. And I'm going to say y is equal to 1250 over x. So the cost is going to be 8x plus 4y, but I'm going to substitute 1250 over x as my y. And now, of course, x has to be positive, and that's 800 plus 5,000 over x. So I want to find a minimum for this sucker. Well, that's derivative. So I'm going to take the derivative, and here they take the derivative by making a negative exponent, because in calculus it's always easier when you have things in terms of exponents, because then you use the power rule, and you crunch, and you wind up getting x is equal to the x squared is equal to 5,000 over 8. So x is equal to the square root of 625, which is equals 25, which is pretty awesome. Now we're going to use a second derivative to decide if it's a max or a min. So the second derivative is positive. That means it's concave up, and that means it's a min. So when x equals 25, that's going to give me my minimal cost. And that's going to give me my minimal cost. And that minimal cost is going to be by taking 25 and putting it into the original, back into the original equation, not a derivative or a secondary, but the original, I get that low cost, that lowest cost is going to be $400. So it's going to cost you at least $400 to encompass that much of an area. But now with calculus, you know exactly what you got to do, and you can do it perfectly efficiently. And that is the story. That is how this all works. Now I want to look at a problem of maximizing revenue and profit. So an office sells 8x permanent markers per year at P dollars per marker. Price demand equation is P equals 10 minus 0.001x. So X is right. So you know what that is. So what price should the company charge for the markers to maximize revenue? And what is the maximum revenue? Well, revenue is equal to price times demand. And in other words, how much you charge times how many you sell. That's a nice way of saying it. So R of X is the price, 10 minus 0.001x times demand, which is X, which is 10x minus 0.001x squared. And by the way, right away, you see this is good. You know, we're going to do calculus, but you can see right away, this is going to be, because that's a negative number, it's just an upside down parabola. So the critical number is just going to be the max. But we'll do it. We'll go through it. We'll whatever. Both price and demand must be non-negative, so X has to be greater than 0. P has to be greater than 0, which means X has to be between 0 and 10,000 in order to make everything work, which is cool. Like I said, it turns out we don't even need all this, but that's all right. Actually, we do, because I want to make sure, we have to make sure the answer we get is between 0 and 10,000. If the answer we get is above 10,000, then it's a whole different answer. Anyway, no, it doesn't make sense. Never mind. The mathematical model for this problem is R of X is equal to 10x minus 0.001x squared. The derivative is 10 minus 0.002x, which means X has to be equal to 5,000. So X equals 5,000, that's going to be the critical number, which I know right away, I'm telling you right now, is going to be the maximum, because like I said, this is really just, I could see that this is just an upside down parabola. And we'll do the official calculus, do whatever, derivative test or whatever. But the second derivative test, if we plug 5,000 into the second derivative, we get a negative number, because the second derivative is just a constant. So no matter what I plug in for X, I just have this constant. So this is concave up the whole way. And therefore, the point we got, 5,000 is the minimum. And I'm sorry, the maximum is, I'm sorry, this is concave down the whole way. So the 5,000 is a maximum. And if I plug 5,000 into the original revenue equation, I get 25,000. And then once X is 5,000, the price is just going to be 10. I just plug 5,000 for X to get the price, and the price is $5. So the company will get the maximum revenue of $25,000 when the price of a marker is $5. I want to look at something that we haven't. This is fun. I just noticed this problem when I was showing you how the math Excel works. I noticed a nice, cute problem here. The product of, find the product of two numbers whose sum is 14. So you have two numbers, their sum is 14, and the product, we want to find the product. So let's go to our, so math, as I said, math is mental abuse to humans. Hope you all appreciate that. And this was what, 4.6. And so we have two numbers, they add up to, what did it say, 14? Are they up to? They add up to 14. And we want to maximize P stands for product, which is XY. So I'm just going to say that P equals X times 14 minus X. Why 14 minus X? Because Y, I can see from this first equation that Y is equal to 14 minus X. And that equals 14X minus X squared. Okay, there you go. and P prime equals 14 minus 2x. Again, I'm just taking the derivative, which means so x equals 7 is the is the critical whatever. And again, I see that this is just an upside down parabola, so it's going to be a max. I mean, you could do all the calculus, but sometimes you just recognize the graph, and will yield a max, and that's and 7 is definitely between 0 and 14. And if x equals 7, then the max is equal to 49, because it's 7 times 7. Because if x is 7, y is 7, so the max just equals 49, which equals 7 times 7, which is 49. So now let's look here. So we want express the given. Oh, what is this? Express the given quantity as a function of x. The product of two numbers x and y. Oh boy, I didn't even say. So it's x times 14 minus x. That's all they wanted. Oh, so I did a lot more than they were asking for. But that's the kind of thing you want. That is the kind of thing you're going to want, is to find the maximum. Anyway, this has been loads of fun, and we'll see you guys next time. And again, if there's any problems that you don't know how to do, you can email me, text me, call me. We could do a Zoom. We could do a private Zoom. I can make a video. Or sometimes I can just explain it in an email. Sometimes it's hard to explain it in an email. I can make a video and post it on YouTube for everybody. I can Zoom with you or whatever it is. I am a human being, and I'm here, and that's what I want to say. Anyway, it has been loads of fun, and I will see you guys all very soon. And this actually concludes chapter 4, and we'll go on to chapter 5. Yay! Okay, bye everyone. See you later.